אוקיי, שלום לכולם. אנחנו יכולים להתחיל. רבותיי, מי שנמצא בכיתה וירטואלית, אם אתם שומעים אותי.
שומעים.
אוקיי, מצוין. אז אנחנו יכולים להתחיל. Okay, so good afternoon to everyone. And the subject of my lecture for today will be conformal transformations. Well, it's a pretty standard subject, and today I'll borrow from the lecture notes of someone that I found online. So his name is Jeremy Orlov, and this is MIT course on complex analysis lecture notes. So I just found them very clearly written and matching more or less what I wanted to say. So I just decided not to invent anything myself, but just essentially copy his notes with a small amendments and additions. Okay, so we mentioned the problem of conformal transformation a few times. Let me remind you that conformal transformations can be informally defined as a functions on the complex plane that preserve the angles between curves. And I'll explain what I mean by this. So imagine that we have a curve on a plane. So this is just a plane with x and y coordinates. And there's a curve on this plane, and we can give it a name. Let's call this curve gamma 1. Okay. Then on the same plane, we can draw another curve, and this curve will given a different name. We'll call this curve gamma 2. And let's imagine that these two curves cross at a point that we'll call this point Z0. Then,
דימית את החומר של לעלות טיפה למעלה? למעלה. זהו, תודה.
Okay. So let me know when you're done.
מה זה אומר that pressure of the angles?
Okay, so that's exactly what I want to discuss.
Okay.
So that's
תודה.
Yeah. So there are these two curves, and we're going to apply a transformation to these curves. So let me just draw this transformation symbolically so we can
כן, סיימתי, תודה רבה.
Okay, good. So let's imagine that we now define a transformation of this plane. So let's define the transformation of this plane to another plane. Let's call, if this plane was a W plane, sorry, Z plane, then this will be a W plane, and the coordinate will be U and V. And will be transformation F that maps Z plane to W plane. And this transformation in general will map any point on the Z plane to the point on W plane. In particular, it will map gamma 1 curve to a different curve on a W plane. So this is an image of gamma curve, and I can denote this image as F acting on gamma 1. So this is the image of gamma 1 if I apply a transformation F to every point, sorry, on this curve. So every point on this curve goes to that curve. Any point on this curve goes to that curve. Then I do the same trick with the curve gamma 2. I apply the same transformation to this curve. So let's say that gamma 2 under this transformation, will go into a different curve. And it will be an image of the curve gamma 2. And this is the crossing point. So this is, let's call it W0. And W0 is obviously an image of the point Z0. So we started with two curves on a Z plane. We applied the transformation F that mapped it on the W plane. And then I'm saying that there is an angle between curves that is being preserved in this transformation. So now let's discuss this point. What do we mean by angle between two curves? How do I define the angle between two crossing curves? Anyone knows how we define an angle between two crossing curves?
Maybe with the cosine theorem.
But how we define it geometrically? Let's look at this geometrical construction, and let's just denote the angle. How we define the angle between curve gamma 1 and gamma 2 at point Z0? What should we do?
We can take a tangential line at the point of intersection for each curve.
So we draw a tangent vector at the point Z0 for the curve gamma 1, and we draw the same. We also draw a tangent vector to the point gamma 2. So we get two vectors. One is touching the curve gamma 1, and another one is touching the curve gamma 2. Now these are two straight lines, yeah? So these are two vectors. And we know that how to define the vector angle between these two lines. Let's call this angle alpha. Then the statement is that if you do the same construction on the plane W, namely you draw a cotangent vector for the curve f of gamma 1 and cotangent vector for the curve f of gamma 2, these will be in general two different vectors. Yeah? But the angle between these two vectors will be the same as the vector as the angle between vectors on the original plane. So this is the statement that the angle is preserved. So now let's see how this is done a little bit more formally. So how do we define a curve? What is the curve for us on the plane? So what is the curve on the plane gamma? How we describe a curve on a plane xy, which we call gamma, a general curve. We normally do it within some parametric description. So we define the parameter. Let's call this parameter t. And any point on the curve is essentially given by two coordinates, x and y, that lies on the plane. So I can think about, as a physicist, I can think about t as a time. So then as time passes, there is a point that goes on this curve and covers this curve. So this is the description of the curve on a plane. Now, how do you define the tangent vector of this curve at some time t or some parameter t? So the tangent vector is obviously a vector with two components. In physics, we would call this a velocity vector. And in mathematics, I just take this curve and differentiate it with respect to time. And I get the vector dx of t over dt, dy of t over dt. This is a tangent vector. So this is the tangent vector of the original curve. And I can look at this thing as a real two-dimensional vector, or I can think about it and identify it with a complex number and say this is a vector on the complex plane that looks like this. So this is just an alternative representation of the vector as a complex number on a complex plane. So this is what I mean by a tangent vector for a curve on the plane xy. So how do I describe a curve which is an image of the curve gamma under the transformation f? Well, obviously, this is given by f of gamma of t. This is the image of the curve gamma after transformation f. And so this is an image of gamma on W plane. And then we can ask, what is the tangent vector for this image curve? Let's call this curve gamma tilde of t. So this would, in this notation, this would be gamma tilde 1, and this curve will be gamma tilde 2. And then the cotangent vector will be d gamma tilde of t, derivative with respect to t. And this will be d over dt, function f of function gamma of function t. And this will be derivative of s times d gamma over dt. And this will be derivative of s. And here will be dx over dt plus I dy over dt. So the components of the cotangent vector are equivalently the same as df over dz, dx over dt. That's the first component, df over dz, dy over dt. That's the second component of this vector. So, okay. So we want to have a transformation which is conformal. That is the transformation that preserves the angle between two tangent vectors. So what did we have? What did we have here? We have a set of two vectors on the z plane, and we have a set of two vectors on the w plane. So in what case these two vectors will have the same angle? What transformation preserve the angle between two vectors? What can I do geometrically to preserve the vectors between two vectors if I have two vectors? Let's visualize this transformation.
אתה צריך לשמר את היחס בטרנספורמציה פשוט, נראה לי.
So one way, if I understand it correctly, is just to scale everything globally. Just multiply all vectors by a number. If you multiply both vectors by a number, they both get bigger or smaller, but the angle between these two vectors don't change. So this is option number one, multiply by a scalar. What is the second choice? What else can I do with two vectors that will transform both vectors but will not change the angle between them?
לסובב אותם בזווית מסוימת.
Yes, rotation by an angle. And now we are looking at the plane as a okay, so let me now see my notes. Okay, so no. So my logic, I will not I will say what I plan to say in a few minutes. What I wanted to do now is to give you an example of conformal map. So just a simple example of conformal map. Example of conformal map. Okay, the simplest example of conformal map is to take a function that multiplies all vectors by the same scale and rotates them by the same angle. So what function does this? It's the function c times z, where c is a complex number. Now, why is that? Because any complex number I can write as an absolute value of the complex number times its phase. So then what this transformation to any point on the complex plane. So if you have a complex plane, and you can think about a vector that goes to this plane. So what this transformation does, it multiplies this vector by a scalar c and rotates it by the angle phi. So a multiplying by constant numbers is the simplest example of conformal transformation. Okay, slightly more interesting example. Consider a map f of z equal to z squared, and I claim that this transformation is conformal. So how do we see it? So look on the z plane. So this will be z plane, this will be x-axis, and this will be y-axis. And let us draw a grid on this axis. So let's draw a grid. This would be, I don't know, black lines. And there will be green lines. So lines, black lines are parallel to x-axis, green lines are parallel to y-axis. So let us see what happens to these lines under a transformation f of z equal to z squared. Okay? So a set of lines that we called black lines, they're parallel to x-axis. So black lines I can describe by z equal to x plus in, x being a real variable and n being integer. Okay, so what happens to these lines under transformation z square, which means x plus in square, which means x squared minus n squared plus 2i nx. So, okay, so let's call a real part of this function u. So this will be a real function. Part of this function will be x squared minus n squared. And imaginary part of this function we'll call 2nx. Okay, and look at what happens. So I now want to draw these lines, these black lines. I want to draw them on the UV plane. So now I want to draw this line on the UV plane. So what is the equation that describes this line on the UV plane? How can I write this equation on the UV plane?
U plus IV.
So I imagine that I have a plane, which is U and V, and I want to draw a curve that was an image of a black curve on a UV plane. So what is the equation that describes a black curve on a UV plane?
Black curve is what represents the X In the z-plane?
So black curve is a curve that is parallel to x-axis, shifted by an integer number. So this is what the black curve looks like on the z-plane.
Well, can't we just substitute x is equal to v over 2n and then put that into u so that...
Correct. And then we'll get u is equal to v squared over 4n squared minus n squared. So what this equation describes us?
A parabola.
A parabola. And this parabola looks like this. So it depends on n. And I'll try to draw. And we decided that these are black lines. Yeah, so I need to draw them in black. So then the black line would look like this. And the next black line would look like this. So this is for n. This is for n equal 1. This would be for n equal 2. And there'll be next parabola going there. And it'll be for n equal 3 and so on. Then, so these are black lines under the conformal transformation z squared. And now we need to repeat the same exercise for green lines. So what do I do for green lines? I'm doing exactly the same. I'm writing an equation for green line. I'm saying green line is described by z equal n plus iy because green line is parallel to y-axis. So under the transformation f of z equals z squared, this thing transforms into n plus iy squared, which is n squared minus y squared plus 2i and y. And I can write a real part, which is n squared minus y squared, an imaginary part, which is v equal to 2ny. And now I want to write an equation that describes the green line. So this equation, by the same logic, will be u equal to n squared minus v squared over 4n squared. It also looks like a parabola, but these parabolas are reflected with respect to v-axis. So if I draw them, I try to draw them. So for n equal 1, the green parabola will start here and will go there. And there'll be a green parabola number 1. Then there'll be green parabola number 2. This is n equal 2. This will be n equal 1. And then there will be a green parabola number 3. And now, okay, I try to do my best, but the point is that if you will now look at the angles between these curves, what must they be?
Right angles.
They must be perpendicular. They must be, yes, 90 degrees, because if the transformation is conformal, the angles must be preserved. So if in the original plane, the angle between green and black lines was 90 degrees, so it must be in this transformed situation. So this is what preservation of angles means. Now I didn't explain how do I know that this transformation is conformal. I just told you that that's conformal, and I more or less drew the lines, and let's call it, I observed by eye that the angle is 90 degrees. Now let's see how do we get it more scientifically. So like we said, tangent vectors for the curve gamma of t at a point are given by derivative and this is the same as x prime of t. plus I y prime of t. So this is a complex representation of a vector. So therefore, tangent vector in a plane is just a complex number. We describe it. So tangent vector for a curve at a given point is just a complex number. That's how we view tangent vector. Therefore, conformal transformation, let me write it. The conformal transformation that rotates and scales the vector is just a multiplication by a complex number. Say so the conclusion that comes from this observation, and that's a very important conclusion, that all analytic functions are necessarily conformal. How do I prove it? So imagine that we have a curve gamma of t that is being mapped by some function f. So the tangent vector to this curve is obviously gf over its argument times gamma derivative. And let's say that we are looking at t equal to t0. And let's call this point gamma of t0, let's call it z0. So this will be df over dz at the point z equals z0 times d gamma over dt at point equals t0. But this guy, df over dz, is just a complex number because we postulated the function f is analytic, so its derivative exists. So this is just a complex number. We can write df over dz at z equals z0 as some absolute value of this function times e phase. And therefore locally, this transformation is nothing else but a multiplication by a complex number, and we know that that must be conformal. So the conclusion that follows from here is that all analytic functions are necessarily conformal function in the domain where they're analytic. Okay, any questions so far? Okay. So if everything is clear, let us briefly discuss the relation between harmonic functions and conformal transformation. So let's repeat.
Dimitri, can I
Sure.
ask a question?
Right, go ahead.
Well, it's about the example that you gave earlier with the straight lines and z squared, yes?
Okay.
We found that the transformation of n equals 0 is undefined. Does that mean that it doesn't exist on the W plane, or?
Let's discuss. I don't remember. Let's look at this transformation.
U equals v squared over 4n squared minus n squared.
Okay, so for n equals 0, the transformation will mean that z is equal to x squared. So u will be equal to x squared, and v is just
equal to 0. Yes.
And v is just 0. So the function, so it means that the function will have only the real part, yeah? So it means that the real axis will become a real axis will become a semi-positive real axis on the u plane. Does it make sense? So let's see. So z is equal to x squared
Oh, I see what you mean. It'll get mapped into the positive u axis.
So we need to add, that means that we need to add to this line, this line.
And what about the other way? Will that get mapped into the positive v to make a right angle?
Let's see. So n equals 0 will map into u. So n equals 0 will map to u equal to minus y squared. So as y runs from minus infinity to infinity, this will map to them. This will map to them. To the negative, I guess.
To the negative v, vertically.
No, to the negative u.
Won't it?
Because
to the negative u. Yeah.
To the negative u.
Doesn't that sort of break our keeping the same angle?
So now there is a problem because now these two lines, now don't have this property, yeah?
Yeah.
They kind of don't respect the property of angle conservation. Good point. I don't know why. Let's postpone it for the future discussion. I suspect that something has happened for this particular point, but
It's okay. I don't want to hold you up too much.
Something here, something subtle with this line, but that's worth thinking about it. But okay. So we said that that's locally conformal transformation is a multiplication by complex number. And we can use it for harmonic functions. So if we go back to our friend harmonic functions, then you probably remember that we have a statement, a theorem that says that if U and V are harmonic conjugates, that is, there is an analytic function G of X and Y such that it's real and imaginary parts are written like that. This necessarily means that U and V are harmonic. Yeah? This implies that UXX plus UYY is equal to 0, and so is V. If you remember, there was a theorem that we have shown, and that theorem says that the levels of U and V are orthogonal. So what we meant by that, we meant that if we look at U as a function of X and Y and draw a map, like map of heights, like people do in geography. Yeah? You will have a plane X and Y, and then on the plane X and Y, you will draw a map of a constant height. Yeah, so if you have a mountain, then you draw a map where this mountain has the same height. Yeah? So once upon a time, when people used geographic maps, that was before navigators. People look at the curve, at the maps, and the maps were full with lines called level lines. So if you follow the level line, you're bound to stay at the same height all the time. So it's the line where function does not change its value. In physics and electrostatics, for example, these lines are called equipotential lines if the function U is electrostatic potential. And so on. So we discussed level lines for function U and V some time ago. And there was a statement that if you will draw on the plane X and Y, the level line for the function U and the level line for the function V, that these level lines, when they cross, they always cross orthogonally. They always cross at 90 degrees. Now we shown this relation using Cauchy-Riemann equations. So this is something that we already know, but now let me use this opportunity and repeat this statement and connect it to the idea of conformal invariance and the idea of conformal maps. So let us consider to eliminate this connection. Let us consider X and Y plane, and let us consider level line of a function U, X, and Y. Let's just say that this function is equal to a constant equal to a on its level line. So what does it mean? There is some curve on this line. Let's make it as a black curve. So there's a curve u of x, y equal to a, and it's a black line on the xy plane. Now let's imagine that we will draw now a level line for the function v of x and y. So let's say that will be a different color. So this will be a line v of x and y, say equal to b. And these lines cross at the point z0. And the theorem says that this crossing must occur orthogonally. Now, how do we know that? Let us look at the function. Let us look at the function g. Let us now look at the function g. So there's a function g. Function g is the function. So remind you, g is defined as u plus iv. So now let us look at the function g and see what function g does to the complex plane. So let us draw the image of a black and purple curve in the u and v coordinates. What is the image? What is the image of a black curve in a uv coordinate? How does it look if we draw an image of this curve in a uv coordinate?
We're trying to draw g, u plus iv.
No, we're trying to draw an image of a black curve in the coordinates u and v. So we are going from coordinates x and y to the coordinates u and v.
Okay.
We have a curve that was a black curve and was equal to u as a function of x and y equal a. And that was in the coordinates x and y. And then I'm going from x and y to coordinates u and v.
Okay, so u equals a will just be vertical lines.
Correct. So it will be a vertical line that passes through point A. And what would be the image of a purple line?
Will be a horizontal line at
will be a horizontal
height
line
B.
going to the point B. So this is the image of these two curves. And now what is the angle between vertical and horizontal line? It's necessarily pi over 2. That's geometrically obvious. So there's a point W0 here, which is equal to the G of 0 naught. And at these points, the image of these two lines are crossing by pi over 2 degrees. But since the map G of x and y is analytic, it means it's conformal. If it's conformal, it means it preserves angles. If it preserves angle, it means that if on UV plane, the angle was 90 degrees, it means that on XY plane, the angle was also 90 degrees. Therefore, this proves that the level lines of harmonic conjugates are necessarily orthogonal. Okay, so that was a nice connection between harmonic functions and conformal properties. We will come back to this towards the end of the lecture today. Now let me formulate another very important theorem. It's called Riemann mapping theorem. So what Riemann mapping theorem says, and I'll formulate it in formal way. So imagine you have a complex plane Z, and on the complex plane you have a simple connected domain D of any shape. That can be any simple connected domain, with the only exception, it's not the entire plane. So it's any domain which is not the entire complex plane. And then the statement is that this domain can be mapped onto a unit disk. So there exists a conformal transformation F such that any domain D can be mapped onto the interior of unit circle, or in other words, onto the unit disk. And what this implies that if you have domain D1 of any shape and domain D2 of any shape, that necessarily there is a conformal transformation that maps one onto another, because each of them can be mapped onto unit disk. So by repetitive iteration, since both of them can be mapped onto the unit disk, it means that any domain can be actually mapped conformally to any other domain. So there is a mapping that maps any domain on the complex plane, or any simple connected domain which is different from the entire plane onto any other simple connected domain. Simple connected means there's no holes in it. Okay, that's a very important theorem. We're not going to prove it, but that's one of the most important theorem of the complex analysis as far as mathematicians are concerned. Very famous theorem. Okay.
דימה,
Yes.
איך זה הגיוני שאפשר למפות כל צורה למעגל?
Well, if it would be obvious, it would not bear name of Riemann. And Riemann would not be that famous as a mathematician. It's strikingly unnatural. It's very mysterious. But what we're gonna do, we're gonna play with conformal transformation for a while and gain some experience and insight and see how this works. But essentially, yes, it's a very strange properties of infinity. How can we take something that looks completely infinite and unbounded and map it into a unit circle? Eh? That's one of the astonishing things.
זה קשור לספירה של רימן?
Sorry?
זה קשור לספירה של רימן?
סקאלה של רימן?
ספירה. רימן ספירה.
Okay, in a way, yes. So the next example actually shows this connection. And that's precisely the point. So let's consider transformation T of Z is equal AZ plus B over CZ plus D. And you know this transformation already. These are, how did we call them?
Mobius transformation.
Exactly. These are called Mobius transformation. Mobius transformations. And mathematicians also call them fractional linear transformation. It's the same transformation. And we already looked at this transformation from the perspective of Riemann sphere, as you correctly suggested. So we interpreted these transformations as the geometrical rotations of Riemann sphere we knew that any Mobius transformation is essentially rotation of a sphere. And then we said, if you have a sphere, imagine Earth, you have equatorial lines, you have, how they called these vertical lines. And if you rotate the sphere, the angle between lines remains 90 degrees. So essentially, if you rotate the sphere, you don't change the angle between any crossing curves. Therefore, these transformations are obviously conformal. I just said it geometrically, but of course, you don't have to think geometrically. You can look at this transformation and say this transformation is an analytic function of z, except some special points. So if this is an analytic function, then it means that locally at each and every point, this transformation is conformal, so it preserves the angle. And this is the only conformal transformation which is in generally conformal. So it's conformal, it preserves the angle on the entire plane. Okay, so let us play with this transformation. Let's pick a particularly simple transformation, but non-trivial. Let's choose a transformation which is a Mobius transformation of this type. Okay, now we can play with this transformation, of course, using Riemann sphere, but we don't have to use Riemann spheres. Let's draw this transformation on a complex plane and see what it does. So I need to draw two things. I'll try to draw them simultaneously. So I want to draw a complex plane as a plane. This is a complex Z plane. And the transformation, the image of this transformation, let's call it W. So on a W plane. And let us see what this transformation does for the upper half plane. So let's take and look at the upper half plane. Why do I like upper half plane? Because this transformation has a pole at z equal to minus I. So there's a pole here. And in the upper half plane, this transformation has no poles at all. So it means that this function is analytic, and therefore it must be conformal. So now let us see what happens with the upper half plane, what this transformation does to an upper half plane where it maps it. Now, any ideas where it will map it? Let's see what your intuition tells you.
So if you take numbers that are bigger than I, then the maps will be on the right upper half of W.
What numbers?
But if you will take numbers that are less than I, between 0 and I, so you will get the map in the left side of the upper half plane.
So let's start with the real axis. Let's take a real axis. Let's use a red color. Where would it go? Let's take a real axis and draw an image on the W plane. So it means that Z equal to X, and it means that it goes into X minus I, X plus I. And X runs from minus infinity to infinity, where this thing goes.
So if you will multiply it by this conjugate number, so you will get.
Okay, let's multiply by conjugate X plus I, X minus I square will be X square plus 1, X square minus 1 minus 2ix. Okay?
So we get that for x less than 1.
So we have
Then
some real part of this image will be x squared minus 1 over x squared plus 1, and imaginary part will be minus 2x over x squared plus 1. And x
But
runs
does
from
it-
minus infinity to infinity. So what is the shape of this curve? Let's see, let's pick some points. So 0 is mapped 0.
So
So
0
point 0 goes to minus 1.
and
Okay.
1 map, plus and minus 1 maps to 0.
Plus 1 makes to minus I. And minus 1 maps to I. Because x equal 1 real part is equal to 0, and imaginary part is equal to minus or plus 1. So it means that these points are equal to.
So if you take,
and the point x equal infinity.
so if you take x equal to 0, you don't get 0.
So
No, sorry, you get minus 1.
And where point infinity goes? If x goes to plus or minus infinity, where it goes?
Well, the imaginary part goes to 0, and the real part goes to 1.
To 1.
Minus 1.
No, plus 1, because it's infinity divided by infinity. Or minus infinity divided by minus infinity. In worst cases, it's 1. And it should be, because plus and minus infinity is the same point. So it's 1. So infinity, so point infinity is mapped into here. So can you guess what shape are we getting?
That looks an awful lot like a unit circle.
Correct. I'll try to draw a circle. That's it. That's the unit circle. So the statement is that you can check if the red line, the real axis, is actually mapped onto the onto the unit circle. Now you can say, okay, if I want to draw a line, another red line, oh, no, let me call it blue line, so to be, that will go to the point I here on this plane. Then I claim that this thing will be mapped on the circle, but it will be a smaller circle. So this is the direction of the line, by the way. And what I'm trying to say that the upper half plane in this transformation will be mapped onto the interior of a unit circle, as I promised. So all points in the upper half plane will be mapped inside this circle. And the further up you go, the smaller circle you will get here. Now, if you would be interested in what happens with the lines that are parallel to y-axis, that this line, we know that by construction, they must be perpendicular, so y-axis itself will be this line. And then if you, so you can visualize a circle that goes perpendicular to the red circle, and the part which is above the real axis, this part will be within the unitary circle, and the part which goes below will be outside of the unit circle. So you'll have circles like that are crossing the circles there. And they will have 90 degrees angles in the image curve, as they have here. So this is the mapping of half plane to the unit circle. Conformal mapping. Any questions so far? Okay, another example of conformal map. A strip to a half plane. So imagine that we are given on a complex plane Z, we are given a strip from 0 to pi, and we want to map this thing onto the half plane. Okay, according to Riemann, it's doable. So we know it can be done. The only thing that Riemann didn't tell us is how it's being done. So we need to invent an algorithm, a transformation that does it. And I claim that the transformation that does it is a transformation e in the power z. Okay, so how do we do it? Well, let's take lines. Let's take a grid. Okay, so I'm erasing. Let's take a grid of lines that are parallel to imaginary axis. And let us take a grid of lines that are parallel to the real axis. And see where they're being transformed. So if I take a line that is parallel to the real axis, I can write it schematically, z equal x plus ia, a being a constant. So this is the line that is parallel to the real axis. So under the transformation is being mapped into the line e in the power x plus ia. And this I can write as e in the power x times e in the power ia. So what is this thing geometrically for any given a? As x runs from minus infinity to infinity. How this?
Phase. You just get phases.
Say it again.
A phase.
Right, but how geometrically I can, if x runs from minus infinity to infinity, what is the geometrical shape of this
So it depends on the value of A, but
suppose I
it
fix
can be
pi over 2.
in the minimum minus E in the power of X, and in the and its biggest will be E in the power of X. So everything you get will be just between those two curves.
But how it will look geometrically?
Maybe we can just continue with the same way we did earlier. We identify U to be e to the x cosine of A. And that's just a number.
So you have e in the power x, e in the power ia. This will be ex cosine A plus I sine A. So it means that U will be cosine A in the power x, and V will be sine A in the power x. And now x runs from minus infinity to plus infinity. So where these points U and V will lie? For a given
a straight line.
Straight lines coming from the
crossing the origins.
Coming from the origin. So you fix an A will be an angle, and for each A you'll get essentially a ray emerging from the origin. So these are the images of the purple lines. Sorry, X plus A, yes, X plus A, purple lines. I was careful with the color. Okay, now let's do the same exercise, but with the green lines. So green line.
דימה, אתה יכול בבקשה לחזור על למה זה המיפוי? כי יש לך גם אקספוננטים, כאילו שאתה ממפה, זה אמור להיות לנים. כאילו, לא?
So these are my points. So my points is e in the power x times cosine A, and e in the power A, in the power x sine A. So an x runs from minus infinity to infinity. So when x is equal to minus infinity, I have an exponent of minus infinity, which is 0. So it means that I'm here at the origin. So at the minus infinity, I'm at the origin, and plus infinity, I'm at infinity. But as I move, so essentially I can look at e in the power x, I can say this is the radius. This is the distance from the origin. As I change x, I change the distance from the origin. So I have essentially my coordinates u and v, if you want, is some radius vector times e in the power ia, which is radius vector cosine A, radius vector sine A. So it's a point on a circle of a radius r at the angle A. And now if I change the radius, if I don't change the angle, I change the radius. So this point goes along this ray. If I change it, if I choose a different angle, I'll be moving along a different ray. Is it clear?
It's better.
Okay, so you just need to practice. It's more or less a question of practicing. There is nothing here that I'm saying it's not. You just need to take and practice it. So now if I take a line which is now parallel to the imaginary axis, and we denote this in green. So let's say that z is equal to b plus iy. So this line goes along the imaginary axis, and the image of this line goes as exponent of b plus iy. So now this will be e in the power b times e in the power iy. So now the radius is e in the power b, and the phase is cosine y plus I sine y. And you change y from minus infinity to infinity. So what will this point do? What trajectory?
It is a circle with a radius of e to the b.
Yes, so now the circle will be circle with the radius r equal e in the power b, and this will be an angle. So now the green line will become a circle of a radius eb. So green lines will be concentric circles, and purple line are radius vectors for these concentric circles, and they obviously perpendicular. And as we expected, perpendicular lines remain perpendicular, and this map, actually what it does, it takes the upper half. Sorry, it takes the plate. It takes the strip and maps it onto an upper half plane. Conformally, which means that angles are preserved. Is there any question?
יש שאלה.
Okay, go on.
לגבי המעגלים, קצת הסתבכתי, כאילו הפונקציות של הזה שאתה נותן גם לקווים הגבולים וגם לקווים הירוקים, זה פשוט משהו שאתה נותן מראש, או שאנחנו צריכים לנחש כאילו את הזווית או את הפונקציה הזאת, כאילו קצת הסתבכתי בקטע.
לא, את לא הסתבכת, זה בסדר גמור. אני כרגע ניסחתי את הבעיה, כך תשימו לב, הפונקציה, לדוגמה, פונקציה c של z ששווה ל-z minus 1 divided by z plus I, what this function does, it conformally maps an upper half plane to a unit circle. Now you can pose two different equations. You can pose equation number one. I'm given a function. I'm given a function t of z. What this function does for an upper half plane, where given function t or any other function maps a given region. You're given a region. You're given a function, and then you ask what this function does to this domain. Yeah. And so here I said, look, this function t, what it does to an upper half plane, it maps it onto a unit circle. But in principle, you can be in different situations, and you can be in a situation when you are, for example, given two domains, and that's a typical situation. You're given two domains, and you ask, I want to find a function such that it maps one domain onto another. And it's a possible equation. That's a legitimate equation. When this equation is, when do we encounter the equation like that? For example, you are given a very complicated domain. You're given a very complicated domain of a very complicated shape, and you want to find, I don't know, some harmonic function that is defined on the boundaries of this domain. Yeah, so it's a complicated domain. We know that harmonic functions and analytic functions are intertwined. They are strongly related. So you want to solve differential equation for a domain of a complicated shape, but instead you don't want to do that. You want to map this complicated domain into something simple, like a unit circle, where the solution is much simpler. Don't worry if you don't understand the details. We will go through this is our next type of problems. But then if you're trying to solve a problem with a complicated boundary, and you say, no, I would rather map this region onto a much simpler region like a unit circle, can I find a transformation that conformally maps a complicated region D onto a simple region which is a unit circle. And then I'm given a region, a domain, which may be complicated, and I need to construct a transformation that maps this domain onto a simple domain. Simple not in a mathematical sense, simple in the sense that it's simple, it allows a simple solution. Yeah. But you can also have a question. I have a function, I have a domain where this function maps this domain. So both equations are legitimate. בבקשה. Okay, so let's see where we stand. So we came to our next subject, which is called symmetry and reflection. But I also see that we have only 10 minutes left, and I don't think there is much point in starting the next subject. So the idea is to connect the properties of conformal transformations with symmetries. In particular with a reflection symmetry. This will be important for us because we're gonna talk about reflections. But I don't think it makes sense to start it now. So let's better postpone it for the next lecture. So in the next lecture, I'll cover the symmetries and connect between conformal transformation and harmonic functions. So we'll come back to the solution of Laplace equation with a complicated boundaries, with a complicated boundary conditions, and we'll perform conformal mapping of a region with a complicated boundaries to the region with simple boundaries, and use it and exploit this for solving differential equations. Yeah, so that's what we'll do next time. I guess it's better to stop here. So do you have any more questions, comments?
Maybe, well, I missed the first couple of minutes of the, so maybe maybe you talked about it and I wasn't here. How do I know if a transformation is conformal? How do I check?
Oh, there's a very simple criteria. I've shown it, that any analytic function is actually conformal.
Any analytic function?
Any analytic function must be conformal. So as soon as you know that the function is analytic in the domain D, it's conformal in that domain. And what it means, it's very simple. So any transformation, if you look at the transformation locally, it's conformal if it has two properties. It takes any vector, and what it does, it either scales it or rotates it. So locally, conformal transformation does two things. It's allowed to scale vectors, and it allows to rotate vectors. So it means that locally, any conformal transformation acts as a multiplication by a complex number. But now if you look at any transformation, say f of gamma of z, and say gamma of t on a complex plane, t is a parameter that describes it, then you can say that this transformation, if you differentiate this transformation with respect to t, is just df over dz times d gamma over dt. And the only thing that comes from the transformation f is just derivative with respect to z. So the only thing that you really need is that the function is analytic and there is a finite derivative. So it means that for transformation to be conformal, you need to have a derivative. And to have a derivative, the function must be analytic.
Does it have to be analytic everywhere? Or does it just
No, it's a local conformal symmetry, or how we call it, conformal symmetry, conformal invariance. That was the name. No, just conformal. So the mapping is conformal. It's a local property. So if you have a derivative at a given point, at that point is conformal. But now you go back to analytic function, and you remember that if you have an analytic function, they will necessarily, if they're analytic in some domain, they necessarily have a derivative within that domain. You cannot have a derivative at a point, yeah? So if derivative is defined, it's defined in some domain. And then what it means that as soon as you have analytic function that at each and every point it has a derivative, therefore it acts as a rotation and rescaling. At each and every point, the scale may be different because the function is not constant, and the rotation may be different, yeah? But nevertheless, at each and every point locally, the transformation rotates by some angle which is point dependent and scales vectors by a scale which is also point dependent. But locally, they all scale by the same number, and they're all locally rotated by the same angle. And this is what locally a conformal transformation do. And to have it, this property, you only need analyticity. Therefore, conformal invariance and analyticity in two-dimensional complex functions, it's practically the same.
I'm going back to one of the things we talked about, like the Mobius transformation, or the transformation that you of z minus I over z plus I,
right?
And there was a pole of the transformation at a certain point, and
Okay,
we didn't really talk about it. Is that a specific? Is it something special, or is it just?
So let's go back to this transformation and discuss it. That was too fast. Yeah. It's probably faster to write it down than to find, huh?
Yeah.
Okay, last attempt. Last attempt if I fail. Ah, here it is. Okay, so there is a special point, z equal. So let's discuss the special point. There is a special point, z equal to minus I. So there is a special point, minus I. And this point is mapped onto infinity. There is a special point is equal to minus I, which is mapped onto infinity. Or for the Riemann sphere, it would be mapped onto the, what was that, North Pole. So yes, this point is mapped to the infinity or to the North Pole.
Which in here would just be an infinitely large circle.
So,
on
no,
the 2D,
on the 2D. That's a point to point. There is no circle. So this point is mapped onto the point that we call infinity. So if you look at it as a Riemann sphere to Riemann sphere, if you look at from Riemann sphere perspective, so let me write it here. So it's our transformation that we choose was z minus I divided by z plus I. Yeah? Yeah. That's our transformation. So if you draw the Riemann sphere, then there is a unit circle here, and there is a sphere above it. So there's a point on the unit circle here, minus I. So when you map it, this point will go here to the North Pole. That will be the mapping. Now, the point minus I itself is a singular point. It's an isolated singularity. Now, if we want to discuss the properties of lines that are crossing at that point, yeah, so the only thing that needs to be clarified is what happens if we look at the complex plane and there's a point minus I, and I look at the lines that cross at this very point, yeah? Whether the angle between these two lines is preserved. And okay, so I don't know how you, so the way I would address this question, I would look at the complex plane, I would map it onto the Riemann sphere, and then these two lines are very well defined because these two lines will be lines on the sphere that go through the northern pole. Yeah, so it'll be two lines, two circles that are going here on the northern pole. So on the Riemann sphere, you'll have a northern pole and you will have lines, circles that are crossing on the northern pole. And what the Riemann transformation and what this transformation will do, it will take a Riemann sphere and rotate it. Okay, I'm not being able to tell exactly what are the angles of rotation, but there will be some axis of rotation, and this thing will be now rotated. Yeah. So we can, and it's obvious from geometric construction that these two circles will remain circles because Mobius transformation sends circles to circles. And it's almost obvious that the angle between these two circles will be preserved. But when I look at it on the Riemann sphere, I know that it's easy for me to see because sorry, I confused. So we start with circles that cross at the point minus I. That's our construction. And they're gonna be mapped onto circles that will be now crossed at the northern pole. That's sorry. They cross on the northern pole indeed, but not on the original Riemann sphere, on the image Riemann sphere. And they will obviously be crossing at the same angle. But now if you will try to project this thing back on the complex plane, so you need to take this thing and perform a stereographic projection on the complex plane. So this point will be infinity. Yeah? So it's hard to draw things in the infinity. So you will be able to draw these lines away from the infinity, but it will be less obvious how you define an angle between these lines. So this will be obviously lines, straight lines. They'll be crossing at infinity.
But you can still define them analytically by d to dz of the.
It's actually a good question. I don't know. It's a nice exercise to do because if there are straight lines that cross at infinity, it means that these actually are parallel lines.
Yes.
Because only parallel lines cross at infinity.
Mm-hmm.
So how do you exactly define an angle of a parallel lines that cross at infinity? Because here we know that there is a well-defined angle. And we also know that this angle is preserved in the rotations. But when you perform a stereographic projection, there's a subtle point there, yeah? I'm willing to say that that's the same angle that is there on one hand, and it's obvious from Riemann sphere construction. On another, from the point of view of a complex sphere, of a normal complex plane, you will have two straight lines that cross at infinity, which from your perspective, they would be parallel. Yeah. So it's a good point. I don't know. It's a nice exercise to check and see how exactly all this works out.
But you can just as well use any other analytical transformation to find the angle if you're looking for the angle specifically. Like say you have two circles intersect at -I, you don't necessarily have to go through the Mobius transformation. As we said, we can just take any analytic transformation.
No, but if -I is not a special point, if there's no singularity point, there's nothing to discuss. Any transformation will preserve the angle.
Yes.
But here there is something subtle, because on one hand, this point is a singular point. It sends it to the point infinity. And now if you define the point of infinity the same way you do it via Riemann sphere, then the angle between these two lines is definitely preserved. But I don't know how you see this property on the usual complex plane. It's something worth thinking about.
Yeah, maybe that's why Riemann is so famous. And
he invented half of modern mathematics, but definitely an ingenious person. Okay, people, I guess it was there's something in the chat, just a sec. Preserve Misham wrote, yes, correct. Thank you. Okay, so let's stop here and see you next week.
Thank you.